Anyway, so I will talk about some methods for dealing with missing data, and I have this listed under 4 headings, and you can read them. It's first useful, I think, to know when missing data can actually be ignored, because then it suggests the sorts of corrections that might be needed, or estimation methods that have some robustness properties that others don't. So if we start with the linear model, and to just allow some generality, consider estimating it by instrumental variables. So think of equation 1 as being a random draw from the population of interest, and then we may or may not observe all of the data that we need in order to estimate this equation by either two-stage least squares or actually even some sort of generalized method of moments procedure. Actually, to illustrate the main idea, just assume that the model is just identified, so we have the same number of instruments as regressors. So you can write the instrumental variables estimator as in equation 2 and then substitute into equation 3. And we've seen indicators that indicate missing data before. One certainly is in the treatment effect literature, where for the people who actually become treated, we have missing data on them because we don't observe the counterfactual in the state where they're not treated. So I'll actually have a little bit to say about how some of these methods apply to that case. Guido's covered it, of course, quite well, but I'll have another couple of comments to make, perhaps. So the instrumental variables estimator, written in terms of the errors and beta, can be written like that. And the selection indicator, SI, simply just takes out the data points that we actually observe. And then the way to think about this is, in general, we should just think of SI as being random, because we don't really know why a particular observation is observed or not. This might be data that's just missing on Y. There might be a covariate that the data are missing on, or some combination. It could even be that we're missing data on the instrumental variables. Okay. So the question is, using this simple representation, when would using what they call in the statistics literature the set of complete cases, when would that produce a consistent estimate of beta? And the weakest condition is given in 4. That's just follows by looking at the final average in equation 3 and asking when would it have a probability limit of 0, and then, of course, by the law of large numbers, that's exactly when the expected value of the a generic element is equal to 0. And so this is it's a kind of zero correlation assumption, but it's not zero correlation in the population. The selected sample the selection indicator matters here. So a sufficient condition, of course, would be to assume that the error term has a 0 mean conditional on the instruments and selection. And then a special case of that is that in the underlying model, the error term has a 0 mean. So this is an assumption purely on the population. And then what would suffice is that selection is based on the instrumental variables. Okay, so that means a deterministic function of the instrumental variables. Notice, of course, in general, that it can't be a function of the regressors, because if those regressors are endogenous, then that's going to violate this condition. So the general, everybody pretty much knows this, I think, that the idea is that if the sample is selected on the basis of exogenous things, then that doesn't cause any systematic bias in estimating the parameters in the population model. But it's a little important to be formal about that, because notice that while this is sufficient, along with selection being a deterministic function of the instruments, it's actually not sufficient if we just impose the zero correlation assumption, which is the one we often use to motivate instrumental variables estimation. So in other words, even if selection is a deterministic function of z, whether it's linear or not actually, because this s times z is not going to be a linear function. Zero correlation is not generally going to be enough. Now, the case where this would be enough is if selection is independent of everything, right? So if selection SI is independent of the instruments and the errors, then that expected value is, of course, the product of the expectations, and then we're done. So this distinction actually comes out in the statistics literature, and I'll talk about these definitions a little more formally later, but if selection is independent of everything, that's typically called missing completely at random. And when selection depends on some observable things, that's, in this case, the exogenous instruments, that's a case of missing at random. In this case, I think we would just call this exogenous selection, and that pretty much tells us what's going on. By the way, this distinction between zero correlation, in this case, and zero conditional mean, this actually does have some implications about whether one wants to use so-called weighted estimators that we're going to talk about later on, even in cases where the selection is a function of exogenous variables. Okay, a special case, of course, is, let's go there. A special case is where we've modeled the conditional mean correctly. It's a linear function of the x's, and then, of course, selection can be a function of x in any way, with the slight requirement, of course, that we have enough variation in the x's so that we can actually estimate the regression function. Now, this kind of derivation extends in a fairly straightforward way to most estimation methods that we deal with. It's easiest to state the assumptions differently depending on what the population object of interest is. So in the case generally of nonlinear least squares, this would be the sufficient condition to ignore selection. If we're doing quantile regression, it would be that the median of or least absolute deviations, which I'll talk about later today, that would be the condition. And then if we're doing maximum likelihood, it's a conditional independence assumption. So in all these cases, you can see that selection can be a function of the conditioning variables, but what it rules out, of course, is selection that depends on the response variable that cannot be explained by the conditioning variables. By the way, showing each of these is easy. In fact, you do it pretty much in one general framework, because in each of these cases, we know that the mean, the median, and the density, or the log density to be more precise, solve an optimization problem in the population. The true parameters either maximize or minimize an objective function that leads to either least squares, least absolute deviations, or maximum likelihood. And so basically the argument is shown in a few steps. I work it through in my textbook, for example. But anytime you can show that in the population you have an objective function that identifies the population quantity of interest, well then multiplying it by a selection indicator and then taking the expected value and using iterated expectations gives you the result. So there's nothing special about these three, except that they happen to be common estimation methods that we use. But something like Poisson regression, which we know is fully robust as long as you have the conditional mean correctly specified, would also fit into this category for exactly the same reason, that the mean maximizes the expected value of the quasi-likelihood function, and it doesn't have to be that log likelihood function is correct. Okay, so clearly if we are interested in estimating unconditional moments, like just the mean, and we try to use the selected sample, then that's going to require that the mean is the same in the selected subpopulation and the unselected subpopulation. And Guido talked about how, of course, you can come up with bounds on these sorts of things if you have a bound on the variable y itself. Okay, now with panel data, exactly the same sorts of things hold. Just to consider the case of maximum likelihood, or I should say partial maximum likelihood estimation, then again we can write this in a couple of different ways, but the point is that conditional on whatever the x's are, selection is independent of the outcome. And again, the way one goes about showing that this is sufficient is to look at the so-called pooled likelihood function. Now notice in this case, this is not necessarily a true likelihood function, because this might not actually represent a joint distribution of the response variable across all time periods, conditional on the x's at all time periods. So this is applicable to lots of cases where we might be using panel data, but we're interested in something like a static probit model, say, or we've put in some lags for a distributed lag model, or even cases where we might have lag-dependent variables, but we also have explanatory variables that might not be strictly exogenous. In all of those cases, you can't write down easily a joint likelihood function. But all that matters is that we're interested in this conditional density. We have it correctly specified, and that being in the sample at time t for unit I is conditionally independent of whatever the response variable is. Okay. Intuitively, this, I hope, makes pretty good sense, and again, the argument about how that goes through is sketched out here and covered more extensively in the notes, but it does allow for some flexibility. Of course, if we go back to this condition down at in equation 7, the more that's in x, clearly the more likely this assumption is likely to hold, because if x is empty, then we're basically assuming that selection is independent of y. That is what the assumption is. If x has, say, lag-dependent variables and other observable variables in it, or at least partially observable variables, then this allows selection to depend on whatever is in x, okay, as long as it doesn't also depend on y at time t once you condition on x. So as you go from models such as static models to models with dynamics, it's more likely that you're going to be able to ignore the selection problem, which in this case, in a panel data case, it might be attrition, units dropping out. It could be attrition where units drop out and you never see anything about them, or it could be people moving in and out of the labor force and you're trying to model labor earnings or something like that. So at this level, this is fairly a fairly general statement. But of course, if what happens is that selection is a function of shocks that occur between time t minus 1 and t to yt, then this condition is going to be violated, and that's why we typically then worry about attrition, say, in panel data, and we worry about people moving in and out of the labor force in a non-random way. Okay, so again, that's a fairly general result, and again, you can see that this would work if we replace this log likelihood function with a squared residual function. Then you can easily write this down in terms of expected values as well, where you're using nonlinear least squares, or you could do the same thing with a dynamic, say, least absolute deviations regression. Okay. So, as I said, this is if we do have a lag-dependent variable, then it does allow selection to depend on y. We don't have to have that. If we, in any case where we think that it really is just a matter of, say, rotating people out of a panel exogenously, then, of course, it shouldn't matter that we are getting different samples on people at different time periods. We should be able to ignore that, assuming, of course, they all come from the same population, and that is implied by this general, very simple result. Now, unfortunately, it's much more difficult to write down conditions in general nonlinear models when you have unobserved effects. Because, of course, if selection is truly independent of everything, then that's easy, because then anything you do, whether it's maximum likelihood where you have some way of removing the heterogeneity, such as in a so-called fixed effects logit or fixed effects Poisson regression, then in those cases, actually, selection can depend on the heterogeneity because you have a way of eliminating it, basically. But in cases where we don't have good ways of removing heterogeneity, which is that entire class of models I talked about on Monday, where you model the heterogeneity as some function of the, say, the time averages of the covariates or other functions of the covariates, you would have to assume that basically selection is a function of those observable things, that what's left over doesn't cause selection. And that's a little unsatisfying, because that leads to basically selection on things that are exogenous, and we don't necessarily think that's always a good characterization. So in general, although there are special cases where one can remove the unobserved heterogeneity and then allow selection to be a function of that heterogeneity, in general that's complicated. But I will work through the linear case with unobserved heterogeneity, just so we can make sure we understand what is allowed and what's not going to be allowed in these cases. Okay, so if we start with this model with, again, time effects and then the additive unobserved heterogeneity, again, thinking of cases with a large cross-section and small number of time periods, and we want to allow for general correlation between, actually in this case, instrumental variables and the heterogeneity, then it makes sense to remove the heterogeneity before using some sort of estimation method. And so we can think of a couple of assumptions that we'd be willing to make, maybe. One is given in equation 11. Now, this is never the weakest form of the assumption that you can write down, but I think it's probably one of the easiest to interpret. This says that the idiosyncratic error at time t, and then this is just the usual conditioning on the exogenous variables in all time periods, but then also conditioning on selection in all time periods, that's equal to 0. Okay, so this is a very clear sense in which selection in any time period is not allowed to depend on the idiosyncratic errors in time period t. So this rules out, for example, the idiosyncratic errors reacting at time t to somebody dropping out at time t minus 1. It also rules out people dropping out at time t plus 1 based on what happened to them in time t, at least if we don't observe the things that happened, which namely are in UIT. Now, what this doesn't restrict is this doesn't say anything about the relationship between selection and the unobserved heterogeneity CI. Okay. This next assumption does make that restriction, because it basically says, in addition to the standard random effects assumption that heterogeneity is at least mean independent of the exogenous variables, it's also mean independent of the selection indicators. So this is more of a random effects type assumption. This is more of a fixed effects type assumption. Actually, random effects typically uses both of these. Well, it does use both of these, although, as I said, you can relax this a little bit. And so this is certainly more likely to be true on its own than adding this along with it. And so if we use fixed effects on the unbalanced panel, that means we can get by with this, okay? Because what happens is the time demeaning now happens, it still happens, of course, within each eye. It's just that we can only subtract off means of the observations we actually have. So in this notation, t sub I here, it's properly considered a random variable, right? It's the number of time periods we observe for unit I. And since we're allowing selection to be random in any time period, then the number of times any unit is in the sample is random. So if you make these definitions, then you can write down the so-called fixed effects IV estimator in this form. And then if you do the simple algebra to get it in terms of the errors, you can see that the weakest condition for consistency is this right here. And again, it's not enough just to say that the ZIs are uncorrelated with the U's. Hidden, this notation, I suppose, is a bit misleading, because hidden in this ZIT double dot is a function of the instruments in all time periods. And of course, that means that the selection indicator is hidden in there as well, in a nonlinear way, actually, because we're dividing by 1 over the number of time periods for each unit. So this is a nonlinear function of selection and the exogenous variables. So you could just assert this, of course, but then you're thinking about, well, when is this going to be true realistically? And basically it's that the idiosyncratic errors are not correlated with selection in any time period. Okay, and then it restricts the exogenous variables as well. Okay, so if we were to do, let's see. Oh yeah, one important point is that this all hinges on this structure where we have this additive unobserved heterogeneity. So remember back to the first lecture, I gave a set of conditions under which the fixed effects IV estimator on a balanced panel would actually be consistent for the average effect under what is not a completely general assumption, but is a somewhat reasonable assumption, at least for continuous endogenous variables. Well, unfortunately, one of the problems with unbalanced panel is that if you just relax the assumptions of the basic model a little bit, and now let's say we add random coefficients instead of assuming a constant beta, then the condition that would be needed for consistency, well, you can write stuff down, but the only thing that would make sense is this doesn't depend on the Z's and the selection in any time period. So if you are worried about that this unbalanced panel would cause one not to be able to consistently estimate the average effect, then it's easy to come up with some sort of test for it. There's no claim that this is somehow the best test for it, but consider this as an alternative where we don't worry about the exogenous variables because we might very well just be thinking of them as independent of the slope coefficients anyway, and we're focusing on, is there a selection problem as it relates to being correlated with these individual specific slopes. And so as a simple way to come up with a test, it seems to make sense to specify that as an alternative. And because we have a large cross-section, we're assuming, and relatively few time periods, of course, we should have units with all time periods, TI. Now, we can't do anything with the units where we only see one time period because we don't have any way of removing the heterogeneity for them anyway. And in the formula, they just drop out. Okay, so one way to implement a test is to take the set of individuals where we have a complete set of data as the base, and then essentially define interaction terms for all the other possibilities, and then just add these as explanatory variables to the equation where, of course, these x's, if they were endogenous before, they're still endogenous, and so this equation should be estimated by instrumental variables. But we have instruments for them because those would just be the ZITs interacted with the same sort of selection indicator. So that's just one simple way to come up with a test for selection problems. The same thing is true if we difference, and we'll actually, in the notes, I discuss this case in more detail because for attrition problems especially, differencing has some advantages because if attrition is an absorbing state, then you know if you see a unit at time t, then you also see that unit at time t minus 1. And so differencing becomes an attractive transformation relative to the within transformation, and you can do some more things with that you can't do with so-called fixed effects. Okay, so here was the comment. I guess I should have saved it, but it's difficult to handle general models with nonlinearities in the unobserved heterogeneity, and I think almost nothing is known, or at least not in any classical setting, where you can deal with dynamic nonlinear models with unobserved heterogeneity. The methods that we have, except in special cases, really rely on having a balanced panel. Okay, so if we think we need to do something about missing data, what can we do? Well, I'm going to start talking about inverse probability weighting, and in the cross-sectional case first. The idea, of course, is to try to re-weight the sample that we observe to make it reflect the population. And the question is, when does that sort of re-weighting work? Well, we already talked about what would happen if we tried to use the mean just on the data that we observe, and that would require selection to be independent of the y's themselves. The general approach to this problem usually uses what's known as a selection on observables assumption. This is a special case of the so-called missing at random assumption, where instead of saying that selection is independent of y when we want to estimate its mean, the assumption is that selection is independent of y conditional on z. Now, this is not necessarily a convincing assumption in lots of cases. So it's important to understand that a lot of methods actually rely on this assumption, or even things that are more complicated than it. Inverse probability weighting relies on it, as do imputation methods that we're going to talk about a little bit later. And so, it may be that this is just a non-starter, and so when you get sampling weights and so on with your data set, instead of just using them as if somehow they've come from some really sophisticated underlying information that we don't have access to, you might be a little suspicious, actually, that one set of weights is being offered to solve any kind of missing data or stratified sampling problem. But in any case, this is a reasonably popular thing to do, so let's go ahead with it and see the kinds of problems it's been applied to. So the idea is to just, this is, I think, the easiest way to think about what's being done that essentially shows immediately why this works. Notice that this average here is over all of the potential observations. So in other words, you think of drawing randomly from the population, but if SI is equal to 0, for whatever reason, you can't use that observation. So the SI selects that out. And then we weight by 1 over the probability of observing the observation conditional on whatever the ZIs are. And it's of course, it's easy to show under this assumption that what this weighting does is if you take the expected value of this, you get mu sub y. And it's an application, not surprisingly, of the law of iterated expectations and then using this condition here. So it's actually quite simple to show that. Now, occasionally you actually know what this probability is. And one case where you know this is in variable probability stratified sampling schemes, where ahead of time some sampling probabilities are decided, and then you say do a telephone survey and you keep an observation with a certain probability. In that case, you actually know these. But in general, they have to be estimated, such as in any scheme where you just are trying to model why some data are missing as a function of data that you actually observe. Okay, so in practice, this is what you do where the p-hats are estimates. And writing the equation like this makes it, I think, a little more relevant for practice because N1 then is just the number of data points that you actually have. Okay? And then this ratio here, this rho hat is the fraction of observations that were kept overall in the sampling scheme. And so this is often the thing that's reported as the sampling weight, okay, where this can be bigger or less than 1 depending on whether the observation had a higher or lower probability than a generic observation. Okay, for actually studying the properties of the estimator, this is a more convenient formulation. Okay. Okay, and of course, this is just a consistent estimate of that fraction of kept observations. You get a somewhat different answer by setting this up as a weighted least squares problem because now the sum of these things actually show up as in the weights, but the how one analyzes these estimators is quite similar. This is actually the formulation that is used for doing regression analysis. So we'll talk about how one does regression analysis in this framework shortly. Now, there are some problems with inverse probability weighting, and I alluded to them already, but there are some problems that are perhaps a little more subtle than what I said, which is that we're assuming that selection actually doesn't depend on the thing we're missing data on. We're assuming it depends on other things that we're not missing data on. This actually comes up in a paper by Horowitz and Mansky, where they studied a fairly simple problem, which was estimating the mean of some function. So whether you call this, you could just redefine this to be y, of course, instead of having it be g of y. But the key is that it's conditional on some other variable taking values in a certain set. So you can call this, I guess I didn't actually write that here, call this the dummy variable d, which is 1 if x is in the set and 0 otherwise. So x could just be something like a gender indicator, and then you want to estimate the mean of something such as earnings for women versus men, for example. And the caution that their paper is mainly interested in providing bounds that you can find, and Guido talked about this actually. But they do mention a problem with these so-called probability-weighted estimators, and that is that in your sample, you usually find weights that are supposed to estimate this. And in fact, this is the rho hat that I talked about, and this is the p hat as a function of z that I talked about. So those are the weights that are reported with your data, where sometimes we don't know what z even was. Okay? But the point is that if we don't know what z was, then we don't know that x was actually included in z. And if you use the probability weights that you get, you actually might come up with an estimated mean that is outside the range of possible values that any logical bounds analysis would come up with. Of course, if this function g of y itself is unbounded, then that's not possible. But in other cases where, if y is a binary variable, for example, then you can come up with estimates that lie outside the bounds, the Horowitz-Mansky bounds that are based on no assumptions at all. Okay, so the solution to this is to basically always make sure that whatever you're conditioning on here is used in calculating the weights. Okay, so this should be conditional on this event, and this should be conditional on this event as well. Okay, then that solves the problem. However, if you don't always observe x, then you can't put it in the conditioning variable z. Okay, so when you get these weights and you're missing data on some x's and you're missing data on some y's, then the weights weren't constructed using those, and you have to wonder, whether they can be used for all kinds of econometric problems. Now, there's a related issue here, and in that if the weights, say, depend again on variable z, and we want to apply regression analysis. So we'd like to estimate the parameters, say, in this population regression. Okay. And we have missing data on either y or x or both, but we want to use these sampling weights in order to do it's called a weighted least squares estimation, but it's with probability weights. We're not choosing weights that are 1 over the estimated variance of y given x. Okay, so the problem is, if we look at the solution to this, so that's written out like this, summed over all observations, and then again, using the same device to select out the observed data points. The problem is that if, in fact, selection is exogenous in this sense, okay, so suppose that selection is a function of the x's, which maybe, includes age or gender or something like that, and maybe we're missing data on those variables for some fraction of the population. But if this is true, then as we just discussed, consistent estimation would be obtained by just ignoring the problem and doing least squares on the observed data. Okay. But if this is true, and x cannot be included in z because x is not always observed, then this condition is probably very unlikely to be true, because the selection, in fact, in a case where selection is a deterministic function of x, it's clear that this can't be true if x is actually not contained in z. So in other words, if we specify some set of variable z, and we go ahead and we estimate a probability of selecting the sample based on z, and then go ahead and do this inverse probability weighting, the weighted estimator will actually be inconsistent, okay, whereas doing nothing would have been consistent. So it's not as if sometimes you hear people say, well, of course, I should use the weights because that can't hurt, right? Well, it can hurt if the weights can't be a function of all of the right things. If in this regression context, if you can always include x in z, then the case for weighting is much stronger, because then it just becomes a functional form issue. Maybe you've thrown some things in z that you don't think belong in the population regression model, but would help to explain, the probability of being in the sample. Well, if only the x's matter, then if you make, with enough data and a flexible enough model, you will pick that out, and so in the end, you won't have an inconsistent estimator. But if you can't include x and z, then that's a different issue. Okay. So this theme actually comes up, unfortunately, in all of the methods that I'm going to talk about. The same issue comes up in imputation methods as well, because if the missing at random assumption doesn't hold, yet you're doing a regression and selection was largely on the basis of the x's in the regression, then it would have been better to not do the imputation, because that'll actually be inconsistent. Okay, I'll mention that again. Okay, now suppose that there's this issue of whether one should use weights if, in fact, we think that selection is what we would typically call exogenous in this case. And let's say we're doing linear regression. Actually, the same sorts of issues come up if we're doing nonlinear regression or maximum likelihood, too. The question is, should we use inverse probability weighting? Well, the answer is it depends. The answer is no if we believe 21 is just the assumption that the conditional expectation is linear. And then if we added the standard homoscedasticity assumption, then clearly we shouldn't weight, because OLS